Prakya.
And
all the other people.
And Nabil. Not really for Nabil though.
he just skips all day.
He's doing an econ skip day. So
Wait, where are they?
what? Nabil's studying econ right now.
Why?
I don't know if he is. Nabil, if you're listening, I'm only kidding because I have no idea. I'm sure you're sick. That's what you told me last time. So
Nabil, we love you.
today we're going to take on another law of thermodynamics. Kind of weird because we have the first law. Next chapter we're going to learn the second law. There is a third law, and I don't know how this happened, but scientists decided they wanted to establish another principle and call it the law of thermodynamics. Instead of calling it the fourth, though, they chose to call it the zeroth law. So this is a number, not the name of a person. Zeroth means like the one before one, or first. Nick? I don't know. It sounds like something the French would do. But this is a great law of thermodynamics. I love it because we can relate to this so easily. When you have two things that are in contact with one another, if they don't start at the same temperature, one of them's warmer than the other one, there will be a flow of heat from the warm one to the cold one. And that flow will continue until the two are the same temperature, which has a fancy name. They reach thermal equilibrium. Once they reach the same temperature, they stop exchanging energy. There's no longer a flow of energy. Can you relate to that? Does that make sense to you?
Yeah.
Put that in your brain?
Yeah.
It's not hard to understand. If I put an ice cube into water, those two do not start at the same temperature. What would you describe, or how would you describe the flow of heat when I put an ice cube into water?
The water's heating up the ice.
Vinny, you had your hand up.
Yeah, the water heats the ice. AKA, the kinetic energy of the particles inside of the water is transferred to the ice.
Right. Who loses heat?
The water.
The water.
Yeah, water is giving heat to the ice, so the water itself is losing heat, and the ice is gaining heat. So you've got the water up here at a higher temperature, the ice down here at a lower temperature. When you put those two together, the water is going to give some of its energy away to the ice, so its temperature goes down. The ice is going to gain that energy, so it's going to melt and then continue to raise in temperature. As soon as those two are the same final temperature, no longer does the water give energy to the ice. They're all the same temperature, so the flow of heat stops at that point. At that point, we have thermal equilibrium.
Not technically like all heat going into this, like doesn't a lot of energy go into melting?
Yes, it doesn't all go into the changing the temperature of the ice, but all the energy is going into the ice, assuming the energy does not go through the walls of the glass that's in. But yes, that's true. The ice doesn't raise in temperature that much because a lot of the energy does have to go to melting the ice. That's true. But it comes from the water. So if I've got a thermometer in the water, I see the thermometer going down, 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 down because the water is giving away some of its heat to the ice. Yeah.
I just want to ask, you know, when you put the ice cubes in the water, and then most of the time the ice cubes are melt down, but people melt with the water. So does it take some of the heat out of from the atmosphere or something?
Yeah, we're assuming, though, all these things have the assumption that we've got an isolated system. Like the water and the ice, you assume that that's in a perfectly insulated styrofoam container where there's no interaction with the surroundings at all. So all the water's heat is not being lost through the walls of the container, but it's going into the ice. Yeah. That's not spelled out here, but that's the assumption that's made. And so we have this expression right here. What can be implied about the signs of these two terms being added? They have to be opposite signs. One of these has to be negative. Do you know which one is going to be negative? Should be obvious, Brandon. Yeah, the one that's lost. There should be a negative term because energy is being lost. If the energy is lost, then what's the sign on the delta? It's negative. Yep. Another way of expressing this, we're not going to be worried about producing gases and expanding gases when we're talking about measuring energy changes using this law. So more conveniently, and I'm using M for more conveniently, I don't mean that. Q gained equals negative Q lost. This is really what the first law, or this is not the first, the zeroth law of thermodynamics says, that when you have an exchange of energy, the amount of energy gained by one thing equals the amount of energy lost by the other. And that allows us to measure temperature, not temperature, heat changes. It is a negative Q lost, yeah. Yep. It's not just take and subtract the delta E loss from both sides. That's what it's going to be. Okay. One side is positive, one side is negative. All right, now I know there's a lot of words there. I'm going to do that first. So this gives us coffee cup calorimetry. Very high-tech. The word calorimetry just sounds like, ooh, we're doing some real science now. Using expensive, fancy equipment, calorimetry. When you're using a calorimeter, ooh, that's good. The whole lab costs less than $5. Yeah, it's the cheapest by far of all the labs that we do. In titration labs, every one of those burettes is about $100. Ooh, man. So that's an expensive lab to do. For a whole class set of 12, add up 100 times 12. Whoa. And then there's 2 classes doing that at the same time. That's an expensive lab for us to do. The chemicals aren't very expensive for that lab, but yeah, with calorimetry, can't get much cheaper than dollar store styrofoam cups and makeshift lids that we just cut out of cardboard and put on the top. So it is kind of humorous, but I'll have to tell you, styrofoam, as cheap as it is an excellent indicator. Insulator. So it works great. You get great results if you're measuring carefully with coffee cup calorimetry. So I make fun of it, but it really is a good technique. We're going to do a lab with Spectrum 20s, spectrometers, and they're a couple $1,000 each. So, and they're, I mean, I only have a couple of them. I'll put it on the roll. It shines light through a sample of solution, and it'll detect how much light goes through, like how much absorbs.
Wait, that wasn't.
Yeah, you did that in GBBE. Yep.
To work $1,000.
What if something happens to them? Are you gonna get mad?
No, he's gonna be so happy about it.
I'll get even.
Bring your grade down to E.
You ever used this equation before? Q equals MC delta T?
Yeah.
The MCAT equation? If you're not familiar or you don't remember, this is a very handy way of monitoring the temperature change of a changing thing and being able to calculate how much heat. Remember, we don't have a heatometer. We can't put something into a heatometer and say, oh, well, this has so much heat. We can only measure flow of heat via changes in temperature. So this equation is used. If we can find out what the change in temperature is of a system or something, then we can determine how much heat, how many joules were transferred or flowed. Yes?
What might the M and the C stand for?
Well, here's what they stand for. So you know the Q is heat. The M is mass. The delta T, I know I skipped one, is the change in temperature. What's the C then?
Speed of light.
No. C is the specific heat capacity. I'm going to use a different color for that one because that's the only oddball term that we have here. This stands for specific. Just didn't want to write it all out. The specific heat capacity is defined like this. This term, the C, takes the other 3 terms and puts them all together. It's kind of like the R does with the ideal gas law. It's the same really thing that it's just a constant that ties all three of those other variables together. It's the amount of energy. So right there, that's the Q. It's how much energy is needed to raise 1 gram, there's our mass, that variable is tied up there, by 1 degree Celsius. There's our delta T. So that's what the definition of specific heat capacity is how much energy does it take to take 1 gram of a substance and raise it by 1 degree Celsius. Every substance has its own specific heat capacity. Who's got a very high specific heat capacity?
Water.
Water does. The highest that I know of. I don't know of anything that's higher than water. So that's something that makes water very unique. Is it's very tough to change the temperature of water. You have to add a lot of energy to get it to change in temperature. Yeah.
So here, like, the temperature is always in Celsius.
Yeah, you don't have to change to Kelvin because we're dealing with changes in temperature. And so the delta T in Celsius is the same as it is in Kelvin because the size of the unit is the same. Okay? So if you go from 0 to 20 degrees Celsius, you're going from 273 to 293. It's the same change, right, in Kelvin. I will tell you this too. In the exercises in the book, you're going to run into, and I think on the practice test and maybe even on the real test, you're going to run into a concept or a term known as molar heat capacity. Have you seen that one yet?
Yeah.
You will. Hopefully not next Tuesday night at 10:30 at night.
Don't look at me.
Had like 2 hours for that.
I just arbitrarily looked at somebody, Sarabi. Don't think that I'm after you.
I had 2 more hours.
Rude.
What is molar heat capacity? The unit, by the way, of specific, so I'm going to go back to this one. Specific heat capacity, if you look at the definition, the unit would be how many joules per gram degree Celsius. It's the amount of energy needed to raise 1 gram of something by 1 degree Celsius. A molar heat capacity would be joules per mole degree Celsius. So there's no handy little symbol for molar heat capacity. They'll just give it to you. And it's just how much energy you need to raise 1 mole of something by 1 degree. I wanted you to see that.
Wait, so how do we like plug it into the equation? Do we just have to do like Q equals M and
The molar heat
delta T?
capacity?
Yeah.
You would just do it like this. Q equals moles times molar heat capacity times delta T. So you're going to have to use moles for your quantity rather than grams.
Okay.
Everything else is the same though. I have an example for you. We're going to do one example of a coffee cup calorimetry problem today. Tomorrow, I'm hoping that I'll have a little bit more to show you tomorrow, and then I'm hoping that we can do a little practice, like with whiteboards. Lab on Monday. We're going to do a coffee cup calorimetry lab. Got to run to make it. I have to make a run to the dollar store to get the equipment. I meant the science supply store. That's what I meant. Did I say something else? All right. This one is in the book. It's not 59. It's 60. It was 59 in the old book. 61.
They use like word coffee cup.
Yeah, they do.
Oh my goodness, that's the one that
Number. Number 61, 62, 63, 64. Yeah, all those use coffee cup calorimetry. So, and I know that several of those are assigned. This one is assigned too. I've already had some people asking questions about this.
I still hate it. I still love it.
Nothing to hate about it.
No.
So we have 2 solutions combined together in a coffee cup calorimeter. 50 ml of silver nitrate, so you have some silver ions, and then 50 ml of hydrochloric acid. What are you going to observe in the cup?
AgCl forming.
Heat release.
What are you going to see?
AgCl forming.
What do you see?
A precipitate.
Thank you. So let's take a look at what this thing looks like and talk. I want you to be able to visualize